soul. Just exit out. Go ahead and get started. All right. We go ahead and get started. We're very happy to have Aditya and Parikh here today. So Aditya got his PhD at Harvard under Matt Reese, and now he is a couple miles from us at Stony Brook as a postdoc. So Aditya is going to tell us a little bit about some dark matter and stellar streams. So please go ahead.
Awesome. Thanks for the invitation and nice introduction. So today I'm going to be talking about probing dark matter microphysics and starting to do this using stellar streams. And really a more appropriate title would be starting to probe dark matter microphysics, because as we'll find out, a lot of the base CDM analyses for a lot of these things have not been done kind of extensively. So the first half of this talk is going to be more based on some of the SIDM overview and work that was done with the authors in the first line over there, Parikh and Matt Reese. And then I'm going to pivot to doing some of the stream analysis and talking more about that. And that's work that's currently ongoing with the set of collaborators in the second line there. And so it'll allude to a lot of preliminary work, which should hopefully appear soon. So just to kind of start and set the stage a little bit, we'll talk about CDM, or cold dark matter, right? So this is a paradigm that's been tested extensively on the largest scales in the universe. So when you talk about correlations in the CMB temperature maps, for example, or large-scale structure surveys and galaxy formation on kind of the very macro scales in our universe, and a whole bunch of other kind of large-scale observations, CDM does extremely well. It explains everything. We kind of don't see any cracks in this paradigm on those scales. But as with most theories, as you start probing and stress testing it, you end up starting to see some deviations occurring. And a lot of these discrepancies end up arising on kind of the smallest scales. Now, these discrepancies that I'm going to talk about are going to be discrepancies between what we observe in our universe today to basically large-scale n-body, like cosmological hydrodynamical simulations of dark matter only. And that's going to be a very important point, that it's a comparison to dark matter only. But taking, for the time being, taking that to sort of be the truth level information about our universe, if we do these comparisons on small scales, we start seeing deviations. To kind of name a few and briefly describe them, there's something called the missing satellites problem, which basically says that if you run an n-body simulation, look at the number of satellite galaxies around something like the Milky Way, and then you go and observe how many satellites we have, we basically see fewer than there are predicted from n-body sims.
Didn't this problem go away?
Good, I'm going to get to that in the third bullet point. So that's that's one. There's the diversity of rotation curves, which basically is kind of the statement that if you look at n-body simulations, you look at systems of various scales, or within kind of like a decade in mass, and you look at the rotation curves that are expected, they look pretty uniform. But if you go and observe real life rotation curves from galaxies or satellite galaxies of the Milky Way, for example, you see this huge diversity in the different types of shapes that you can get. And then there's also things like the core versus cusp problem, which is basically just a statement about the expected density distribution of dark matter in galaxies compared to observations. Now, to Marius's point, some of these problems have gone away, and they've gone away for a variety of reasons, right? So things like the missing satellites problem, for example, have gone away just because we didn't account for observational biases properly, right? So as you go to smaller and smaller scales, these objects are harder to see, and observationally, as we have improved and made telescopes better and more precise, we've increased the resolution, we've been able to find a lot of these galaxies or satellites that were missing. And then the other kind of problem is that, just in general, baryons are difficult. So as I mentioned, these discrepancies that we're seeing are between simulations that only contain dark matter to things that we observe in the universe, which very clearly have baryons. And just in general, doing kind of large-scale simulations with baryons are, generally speaking, difficult, because we don't have very good first principle understandings of a lot of like the baryonic feedback prescriptions that go into these large-scale n-body simulations, and many times we just kind of tune these parameters so that we end up getting something that looks realistic, in the end with our simulation. But there's kind of no first principles calculation of saying that, okay, this is exactly what the supernova feedback rate should be, or this is exactly what, the cooling rate due to baryonic interaction should be, and how that relaxes dark matter density profiles and things of that nature. So, there is an ongoing debate between how much of this is new physics, how much of this is just baryons and not understanding baryonic physics correctly. As a theorist, I like to not take side in this debate because it's hard to answer any of these questions kind of conclusively. But I like taking more of a theorist approach to this problem, which is basically everything that we have observed in the universe, so all of the baryons, theoretically they all have interactions, and we've observed all of these interactions. So even things like neutrinos, which interact super weakly, we've seen that they at least have some non-trivial interactions, right? So it would be really weird if you have an entire sector of the theory that dominates the matter density of the universe today, just be completely inert and not have any kind of interactions. So just kind of, as a more abstract approach to this problem, it's very reasonable to expect there to be interactions in the dark sector. And so then the question is, how would this manifest, right? So what I'm going to show here is, as a function of velocity, a map of the expected velocity-dependent cross-section per unit mass. And so what the idea here is that if you look at the density profile of various objects on various scales, so in green we have clusters, which are some of the most massive objects we have. And then as you go down, you have low surface brightness galaxies and dwarfs. If you look at the density profile of these objects, you can infer what type of self-interaction cross-section would be required to basically create this behavior. And so you have sort of this distribution of expected measurements, if you want to call it that, or basically inferred measurements of what the self-interaction cross-section would be. And then this paper back in 2015 basically said that, okay, if we have a long-range Yukawa potential, we can sort of fit it. But even by eye, you can draw a whole bunch of other curves that kind of go through this data, right? So it's not unique in some sense to say that the long-range Yukawa potential is the only thing that works.
Yeah, can you explain what you mean by the required cross-section to fit observation?
Yeah, good. So when I say required, what I mean by this is, of course, all of these things should all go all the way down because everything is still nominally consistent with CDM. Depending, with the asterisk being, it depends on the underlying baryonic feedback mechanism that's going into how you infer whether CDM works or not. But the basic idea here is, if you look at the density profile of these objects, you end up finding that at some point these objects all tend to core out instead of being cuspy. And the idea is then to say that there is sort of a specific radius below which you're going to core out because the self-interactions are efficient, and outside of which self-interactions are not efficient, so you're NFW-like. And the basic idea is that if that's sort of the story that you're gonna tell, then that tells you what required cross-section you have. And in particular, these gray dots over here are actually doing exactly this in n-body simulation, which is basically to say you run an n-body simulation with a cross-section of 1 centimeter squared per gram, constant velocity, look at what the density profiles of these objects look like, and then try to run this pipeline of saying, if I saw this in real data and I didn't know what the cross-section was, would I be able to infer it back out? And they do reasonably well, so you can then apply it to real systems. So in both of these cases, or in this data here, you can even tell, like just by eye, you could draw a whole bunch of other curves that look like they fit this data. And the other thing to note is that you're at extremely low velocities, and as you get to smaller and smaller objects, the inherent velocity dispersions of these objects are really low. So on average, the dark matter particles are moving very slowly, and if you have a long-range interaction, then you can often get the Sommerfeld enhancement to occur, where you can basically boost up the cross-section due to small scale, due to this long-range force. So what exactly is Sommerfeld enhancement? It's often easiest to understand this with a classical analogy. So imagine you just have a disk of radius r and some particle that's moving at velocity v. If you were to compute the cross-section, it's just going to be the geometric cross-section. If there's no interactions or anything attracting this object to the disk, it's just a geometric cross-section, either you hit it or you don't, and it's just pi r squared. Now instead, if you turn on some kind of attractive force, so imagine this is like a classical mechanics problem, you have a comet that's falling in towards the sun, so you have gravitational interaction that's taking place, and you compute the cross-section, you find that there is actually a maximal impact parameter where if you're below that, you're always going to fall into the sun, and if you're above that, you will kind of glance off and go off to infinity. And if you rewrite it in terms of the original parameters of the problem, you basically find that it's this sigma naught, so this pi r squared, times this enhancement factor in parentheses, which scales inversely with the velocity of the particle. So as you go slower, you're more likely to hit it. And this is, this should jive with your intuition, which is basically that if you have a really slow moving comet, it's much more likely to hit the sun than if it's, whizzing by really fast through our solar system. It may deflect a little bit, but it's basically going to kind of continue unperturbed. So more concretely, what exactly is Sommerfeld enhancement? It's a non-perturbative effect, but it can be treated quantum mechanically. And what I mean by that is what ends up happening is your naive perturbation theory breaks down, where you just say, okay, a tree level cross-section is sufficient to describe this physics. What you actually need to do is sum up all of the loop diagrams that come along for the ride. And the most dominant contributions come from what are called ladder diagrams, which is basically just multiple exchanges, 1, 2, 3, and so on and so forth. You have to sum all of them up. And the way to do this in a much more straightforward language, so there is a way to do this in field theory, and there's approaches of doing this in field theory. But there's a much more straightforward way of doing this, which is you take your tree level potential, you map it to a you take your tree level scattering amplitude, you map it to a quantum mechanical potential, and then you just solve the corresponding Schrodinger equation, and it basically sums up this family of ladder diagrams for you. So as two case studies, we're going to take scalar interactions and pseudoscalar interactions. So scalar interactions give you kind of this, tried and tested Euclid potential. Pseudoscalar interactions give you this gigantic mess, and it begins with two important things, or really three important features. One, there is two delta function terms that come along for the ride. One of these is just coming from the fact that you can also have a leading order S-channel exchange for the particular process that I'm looking at. The second delta function term here actually comes along even if you just have T-channel exchange, and if you're careful about taking these derivatives, that kind of just pops out. The other thing to take into account is that you have a 1 over r cubed behavior, and you have a operator here that preserves total angular momentum, but does not conserve individual orbital angular momentum or spin, because those two are coupled. So now the question is, how do you set well-defined boundary conditions for r to the minus 3, right? So the standard way of solving the Schrodinger equation in quantum mechanics is you define some boundary conditions at the origin, and you basically just solve the Schrodinger equation out, and at infinity you can extract out what the S matrix looks like, and that gives you that'll give you the S matrix for the scattering that you're considering. But if you have a 1 over r cubed potential, it's actually not possible to do a well-defined set of boundary conditions at the origin. And this is where a lot of our intuition from QFT will actually come in and basically save the day. So when what we devised was a new matching prescription, which basically leverages the fact that when you're very close to the origin, so basically if you're within the Compton wavelength of the particle, your particles are actually moving semi-relativistically or even relativistically. And so your quantum mechanics is a non-relativistic expansion of quantum field theory. And as a result, you shouldn't expect quantum mechanics to actually do a good job in this region right here, right? So what we said was, okay, what we're going to do is we're going to trust quantum field theory in this region here, use that to set boundary conditions at some matching radius. We chose it to be the Compton wavelength of the particle, but you have some freedom where the physics that you get out at the end is independent of exactly where you're doing this matching. So you can vary this matching by an order of magnitude up or down, and you basically get the same physics to pop out at the end. And you use quantum field theory here because that's a better description of the physics. And then in the large distance limit, you just switch back to doing quantum mechanics because that's a better description of the physics in the long range. And it'll capture all the Sommerfeld enhancement that's occurring because that's really a large distance effect that's occurring.
Is this different from what people usually do? What you're saying?
Yeah, so usually what people do is they'll take A to be 0. So they'll set the boundary conditions at the origin, and they'll set both the wave function and its derivative to be something at the origin, and then just solve the Schrodinger equation out. And this is part of the reason why basically no one had accurately solved the pseudoscalar case up until that point. Because the minute you try to set boundary conditions at the origin, you end up needing to do some kind of renormalization of your Schrodinger equation. And if you don't do it carefully, you often end up getting false conclusions out, which is what some of the previous work had ended up doing.
I mean, relatedly, I heard a recent talk by Tracy, and I think she did something similar. Do you know the differences between like her prescription and this is?
So that's also work with me.
Okay.
Yeah, so we're working on, it's actually leveraging basically the same idea. The only difference is that in this entire story, I'm just talking about scattering, and scattering is really nice because everything is Hermitian and everything's fine. Probability is conserved, you're not leaking it anywhere, and so you can basically do the entire analysis without having to worry about non-Hermitian components to your Schrodinger equation. So the added complication with the work with Tracy is that you need to factor in these non-Hermitian terms carefully, otherwise you end up getting unitarity violation.
At what point? Like, when does that become important? Remind me.
Sorry, what?
You said like when do these non-Hermitian terms become important?
Yeah, good. So the non-Hermitian terms become important because if you don't carefully include them, basically what ends up happening is that your Sommerfeld enhancement will naively just boost your annihilation cross-section past the unitarity limit. Right. And so if you incorporate them in carefully, you'll basically help regulate that and bring it back down to like basically preserve unitarity and not violate it.
Thanks.
Okay. So I talked about using the QFT description to kind of set the boundary conditions. What I'm going to do is I'm going to actually use the first Born approximation as a proxy of doing that. And so over here I'm just showing the fact that regardless of what velocity that I'm looking at, if I basically take the first Born approximation and if I just take the tree level QFT calculation in all three of these different cases, I basically faithfully reproduce exactly what's happening. So if I do, if I trust the fact that my firstborn approximation is going to faithfully reproduce tree level QFT, I can compute this K matrix, which is basically a multi-wave or like coupled channel case generalization of tan delta L, essentially the phase shift. And then once I have this, I can basically use that to determine how the wave function and its derivative gets modified at my matching radius. And then once I have that, I now have the boundary conditions at r equals a to then solve the Schrodinger equation out from there to the thing. So what so then with that in hand, we can basically look at the two test cases that I talked about. So we first start with the scalar exchange. So here in blue, I'm plotting the numerical cross section. So that's doing this entire matching procedure that I just described, and then extracting out what the S matrix looks like at infinity. And then in orange is just the QFT tree level cross section. And so what we see is that at low velocities, there's a very clear enhancement. As we get to higher and higher velocities, these two things actually start to lie on top of each other, which is exactly the intuition you would expect from having Sommerfeld enhancement. And the other interesting thing to note here is that there's actually a third curve that lies exactly below this. And that third curve is actually just computing the cross-section by, instead of doing this whole matching prescription that I just described, the Yukawa potential is really nice because it actually gives you a non-singular, well-defined Schrodinger equation. So you can actually just set the boundary conditions at the origin, forget about this entire matching prescription, and just compute on your merry way. And what ends up happening is that those results basically match exactly what we get from doing our matching prescription. So the point being here that we're not actually losing any of the physics, and we're actually preserving the accurate description of what's happening at those short distances.
Sorry, doesn't that mean the old way that people were doing it was getting the correct answer?
For the Yukawa case, yes.
I see, but not for
pseudoscalar case.
I see, so you'll show comparisons later.
Yeah, so I mean, I'll flip to the pseudoscalar results right now, and what I'm showing here is again the same thing. The problem is that here you basically can't set the boundary conditions of the origin without doing some kind of renormalization, and so if you're willing to do the renormalization properly, which a lot of people have not done. So in the literature, basically there have been kind of 2 or 3 papers that have tried to address this problem. One paper basically just said, I'm just going to take a 1 over r cubed potential and just solve that without taking into account any of the basically not taking into account any of the coupled channel behavior of the actual pseudoscalar potential, and I'm just going to ignore the fact that I need to do this renormalization properly at the origin. So that was one paper, and then there was another paper that tried to do this by actually regulating the behavior at the origin by introducing a square well. The problem with that, and I'll mention it again a little bit later, is that they basically didn't actually match the square well to the underlying pseudoscalar QFT that they had written down. So basically the depth and the width of that square well was allowed to float freely. And so you end up getting these Sommerfeld peaks, and you're led to believe that there is Sommerfeld enhancement. And the reason that that doesn't work is because what's actually happening is you're getting these near threshold bound states of the square well. But those are not, if you had matched correctly, you would end up finding that the square well doesn't actually permit any near threshold bound states. So as a result of that, you basically end up kind of fooling yourself into thinking there is Sommerfeld enhancement, and in reality there isn't. So for the pseudoscalar exchange here, again, I'm showing the same thing. There's the numerical cross-section in blue, so that's using our matching prescription, and then in orange, there's the QFT tree-level cross-section. So you end up finding that the behavior looks exactly the same all the way out, and there's a slight discrepancy out at beta of 0.1, which numerically amounts to about a 1% discrepancy in the cross-sections, and that's coming entirely from the fact that when I compute the cross-section, I'm taking the tree-level leading order in beta expansion of the amplitude, and so the next order correction would be an order beta correction in the potential, which will manifest as an order beta squared correction in the cross-section. So the deviations at large velocity are basically being entirely contained by the fact that my non-relativistic expansion, I need to include higher order terms to capture that behavior. So, it may be surprising that there's no Sommerfeld enhancement in this story. After all, if you look at the potential, you see pieces that look roughly like the Euclid potential that we had, right? So what I can argue is that sort of heuristically, this is basically a short range potential. And the way to see that is, first of all, the 1 over r cubed piece here and the 1 over r squared pieces, they'll basically fall off too quickly to really support any kind of long range behavior. And then there is this piece here with scales like 1 over r, and this piece here with scales like 1 over r. And what you end up finding is that for that to have any kind of long range behavior, you need your mediator to be light. And that's exactly the regime where this m pi squared over m pi squared will basically suppress each of those Euclidean terms. And so essentially the pseudoscalar exchange potential will basically behave as a short range potential for essentially all parameter values, unless you go non-perturbative in alpha. We can do this a little bit more rigorously. So again, as I mentioned in the beginning, this is it's a non-perturbative process, and the idea is just that your expansion in alpha is not correct. You really have an expansion in alpha over b. And so what you can do is just estimate how big the one loop process looks compared to the tree level process, and if these things are comparable, you end up not having to worry about including them, if they're comparable, you have to worry about including all of them, and if the one loop process is suppressed, you don't end up having to worry about it. So for the pseudoscalar case, you end up finding that when you take this ratio, it basically scales like a log of the mass ratio, and so in general, you are not going to have to worry about doing any of this resummation. Whereas if you do the same analysis for the scalar case and you take the ratio, in a non-relativistic limit, the T-channel process at tree level is the dominant one, and so when you take this ratio, you end up finding that it's relevant when m phi is less than alpha m pi. So this basically tells you that when the range of your potential is longer than roughly the Bohr or the Compton wavelength of the particle, the Bohr radius of the interaction, then you end up being in a case where you need to worry about this. And this is one of the familiar conditions that is often stated in the literature for when you have to worry about including Sommerfeld enhancement or not. Right? And so now going back to your question, Josh, about whether these things have phenomenological implications or not, the first question is just, I was able to do this entire analysis without ever having to worry about this, like the apparent singularity that's occurring at the origin. And so that kind of begs the larger question of, is this potential actually singular? And more broadly, do singular potentials have any place in explaining, physics or like phenomenology that we see? And to that end, there's extensive reviews in the literature that have often tried to approach this problem of characterizing, field theory, like operators in field theory to potentials in quantum mechanics. And there's some that have tried to do this by just looking at like operator dimensionality. There's also things that have tried to do it just by, looking at the divergence behavior as you get to the origin. And I'd argue that both of these are incorrect. The first one, which is looking at the divergence behavior at the origin, the pseudoscalar potential is a clear example of something that diverges faster, but it's not singular. And then there's additional, I'll talk about it if there are questions. I can talk about it. I have some backup slides on it. But even if you have non-renormalizable operators, you end up being in the same regime where if there's kind of a well-defined tree-level QFT description of where this is descending from, then it doesn't matter that the operator in QFT is non-renormalizable. It will still give you, a well-behaved, non-singular quantum mechanical potential that you can evaluate. And then, as I had already sort of mentioned to Josh, there have been some papers that have claimed that these non-renormalizable operators have implications for SIDM and Sommerfeld enhancement more generally. And essentially the pitfall that they're kind of falling into is that these square wells are not being, they're not matching onto the underlying field theory properly. They're basically allowing it to kind of float freely. And so you're getting this enhancement or this behavior to show up when you are essentially in like a non-perturbative regime where you would expect the one loop process to be important because your coupling is just too big.
Which paper is
I can find the reference and tell you. I don't have the only author that comes to mind is Junior, and I don't want to throw him under the bus. So, but I can probably find the senior person on it and send it to you if you're interested. Okay, so I developed this entire formalism of talking about self-interacting dark matter and how to compute a scattering cross-section properly, including things like Sommerfeld enhancement and all of these non-perturbative effects, which are generally difficult to kind of deal with. So now the question is, where can these effects manifest, right? So is this all just going to be some slight deviations in, for example, or is it just going to be some slight deviations in the density profile of galaxies that we may or may not have under control to begin with, or are there other places that are relatively more pristine and nicer kind of dark matter only environments, if you want to call it that, where these effects can manifest? So there's going to be two observables of interest that I'm going to focus on. The first is this thing called the subhalo mass function. So the idea here is that if you take a galaxy like the Milky Way and you just count the number of different objects of different masses, you can basically, as a function of mass, you can plot the number of these objects. And so that's called the subhalo mass function. And on basically the heaviest scales, all of these things look roughly the same. But as you go to lower and lower masses, you end up seeing these deviations which can occur. So this is taken from a paper where they ran a CDM-only simulation and then compared it to 3 different SIDM simulations. So there's the green is an SIDM simulation with a 1 centimeter squared per gram cross section. The blue is 10 centimeters squared per gram, and then the red is a velocity dependent cross section that turns over at approximately 100 kilometers per second to sort of mimic more realistic underlying theories where you actually have this velocity dependence manifest. And what you end up finding, again, is that as you get to lower and lower mass scales, these deviations start to become relatively large. And this is one of the places that these effects can manifest. But there's difficulties with these objects that are super light, and the main difficulty is that they tend to be dark. So observationally, it's very difficult to detect objects that are like 10 to the 6 solar masses, or even sometimes 10 to the 7. That's kind of, I believe that's currently where our limit is on light objects surrounding the Milky Way. And the main reason is that these things are just not very efficient at forming stars, so they're just not luminous. But again, these are basically the places where we're going to see the most pronounced effects. The other place that these effects are going to manifest is if you were to map out what the density profiles of these objects look like, specifically the really, really small ones, they'll often be core collapse. And so the basic idea here is kind of the story of gravithermal core collapse. And so the idea is that if you start with an initially NFW profile, or a tidally truncated one, or a truncated one or a tidally stripped one, but basically if you start with some kind of profile and you allow self-interactions to occur, then more or less it will follow through these steps. It's just that depending on what initial profile you start with, the timescales of these steps may be different. But the idea is that initially the inner regions tend to be the densest, and therefore self-interactions are efficient within these inner regions. So that allows you to start thermalizing and increasing the temperature, and that starts kind of what's called a core expansion phase. And then at some point you form an isothermal core and this expansion halts and then basically reverses. And at this point it's a runaway process through core collapse, and it basically starts becoming denser and denser. As it contracts, it gets hotter. But it's sort of self-similar evolution. So this behavior is kind of the same whether you're in a 10 to the 6 solar mass object or like a 10 to the 10 solar mass object. As long as you're kind of in this core collapse phase, the core collapse is going to be sort of independent of the mass. And then eventually you'll enter the short mean free path regime, and at this point the core starts becoming optically thick to these self-interactions, and this is kind of where it plateaus in its maximum mass. Now, all of these things are, of course, proportional or related to the cross-section that you're allowing. And so, in general, as you get to smaller and smaller objects, their velocity dispersions tend to be lower and lower, and as a result, their cross-sections will be higher, partially boosted by things like the Sommerfeld enhancement, and also just boosted by the fact that most realistic models that you can write down across of self-interactions are that also fit the data will have a behavior where the cross-section increases as you go to lower velocities. So in general, this gravithermal core collapse is going to be much more efficient for the smaller objects, which also happen to be the things that we can't see. So this is where the stellar streams start coming into play. And the idea here is we want to basically use streams as detectors. As messy as they are astrophysically, once an interaction occurs, there's not a lot of additional evolution that's occurring to that object that's not governed by orbital dynamics, which is basically deterministic to a large extent. So the idea is just that you have some kind of interaction occurring, and it'll just get preserved in one of these streams, and then you can let it evolve to today and look at what that looks like, compare it to the actual stream, and see what happens. And so this is a map of all of the streams that have been detected to date around the Milky Way, and with their apparent positions on the sky, sort of accurately labeled there. And then the width of these streams is actually a measure of the internal velocity dispersion of the stars that are making up the stream. So basically, the thinner they are, the colder they are, and the fatter they are, the more randomized the motion is, essentially. So, as a theorist, I like to do cartoons because real astrophysics is very hard. So just to kind of schematically explain what's happening here, right? So imagine you have the galactic center. This black arc here is a depiction of my stellar stream, and then I have some dark subhalo that's moving at some velocity v. When you have this behavior occurring, you will basically cause a differential acceleration along the entire arc length of the stream. And if you were to basically integrate that over the entire time of the encounter, you'll basically get the impulse that's imparted by the dark subhalo on this stream. And it's convenient to sort of define this coordinate system where I have perpendicular or radial to the stream, I have parallel or tangential, and then orthogonal, which is coming out of the page. And basically, it's it's much more convenient to actually decompose these accelerations along this coordinate system, and I'll explain why that is in a few minutes. But once I have that, what I can do is I get sort of this characteristic shape, where basically there's a part of the stream that gets pushed away and there's a part of it that gets pulled towards you. And that's roughly what's going to happen in kind of 2 out of the 3 directions. And in the third direction, it's going to be pulled in just one direction because you're either going below the stream or above the stream in one of the 3 directions. So that's why the third kick curve, in this case the orthogonal kick curve, only looks, only has kind of 1 peak instead of 2. So once I have that, what I can do is characterize this kick curve by basically 2 parameters. So there's this thing called delta mm, which is basically the peak-to-peak difference in the delta V that's imparted on the stream. And then there's this variable f peak, which is basically the ratio between the distance from the peak to trough distance divided by the entire arc length of the stream. And that's a measure of essentially how concentrated the interaction is. So, if you have a very puffy object that's kind of disrupting the entire stream, or do you have a very small, object that's kind of just doing a concentrated effect in one part of the stream. And then what ends up happening is that if you have this type of behavior, you end up getting, just very schematically, if you look at the stream, this is kind of an idealized version of what the stream looks like because I've not included any of the inherent velocity dispersion. But what happens is you end up getting kind of this underdensity forming here. And that essentially will manifest as what's called a gap, right? So as I mentioned earlier, we define, instead of doing kind of galactocentric coordinates, it's easier to define coordinate systems on the stream. And the reason for that is basically because if you look at a realistic stream like GD1, there's essentially 2 features that people often talk about as smoking gun signals for why these interactions are expected to have occurred and why they're important. So there's a gap, which is basically literally what I'm showing here, where you essentially just have a underdensity of stars at some point along the stream. And then there's another feature called a spur, which is basically, instead of kind of following this arc perfectly here, you would basically just have sort of a outward push of what's happening. And the way to map that into these dimensions here is that the gap is predominantly going to be formed by impulses in the parallel direction. So basically, as you push things away from each other, you're going to form this underdensity that's going to manifest. And then spurs are going to be forming due to perpendicular impulses. Basically, as you push things out from the track of the stream, they're going to end up getting a different period and therefore have a slight deflection in where they're arising. So, So in general, you have these 2 variables that sort of characterize what's happening. There's a slight asterisk here, and the asterisk basically comes from the fact that there's sort of a flat direction. If I just focus on gap evolution for the time being, there's also a flat direction that's occurring because you have a degeneracy between the size of the impulse and the time at which the interaction occurred, because basically these gaps will grow over time. Once you provide an impulse to some of these stars, they'll basically keep moving outward along the stream. So there is sort of a degeneracy where if the only variable you have is the size of the gap, a larger impulse a shorter time ago versus a shorter impulse a longer time ago can produce effects that look roughly the same, right? There are ways of breaking these degeneracies, and in general, if you had full 16 phase space information, so not just the positions, but if you also had velocities, you might be able to kind of back out how large these, how large the impulse should have been just by looking at stars kind of at the edges of these gaps and looking at, how much larger their velocities are relative to the rest of the stream. But in general, there's kind of this degeneracy that is harder to break unless you have additional information feeding into the problem.
Don't you have velocities, or at least some components?
At least for some of them. So this is for GD1 in particular, we do, but for the the entire catalog of streams that I showed, we don't actually have all of this information. So it is, in general, you would want to do like a global analysis of all of these streams. For the time being, we're just focusing on GD1, but in general, you would want to do a global analysis of all of these streams, and at that point, you would need this data for the rest of them.
I thought like to even identify a stream, like they're somewhat encoded by you have all these stars with the same velocity or very close to the same velocity, right? This coldness. So don't you have to use velocity to even identify these streams, or?
In general, I think the largest amount of discriminating power for actually identifying a stream comes from looking at these stars in like different filters and different bands, because basically all of these things originated from the same globular cluster, and therefore they should have essentially the same properties of like metallicity and age and all of those things. So I think the largest discriminating power comes from that, and then if you have enough objects that are still there, then I think the velocity information is kind of like a second order effect to identify. Okay. So there's certain questions that we have. For example, what are the distributions of these two variables, delta mm and f peak? How many such events do we expect? And in general, what can they tell us about subhalo properties? Because at the end of the day, being able to recognize that these interactions have occurred is great, but if they don't tell us anything about the underlying subhalo properties, it doesn't bring us any closer to actually addressing kind of the dark matter microphysics. Right? And so in literature, there have been basically two approaches at essentially opposite ends of the spectrum. So there's been purely analytic approaches. So this paper is just one example, but there have been a few papers that have kind of tried to approach this problem purely analytically. And so essentially their idea was just to say, suppose I have a stream that's infinitely straight, moving in the y direction with some velocity vy, and then I have a subhalo that has some impact parameter, some mass, some basically take it to be like a Plummer sphere of a certain mass, certain scale radius, and so on, and have it fly by with some velocity information, and then you can end up getting these kick curves that I was showing earlier, where you can actually relate things like the height of these peaks and the width of these peaks and so on and so forth to basically the underlying parameters of the impact geometry and the subhalo that was doing the perturbing. So there have been purely analytic approaches that have done this side of the story. And then there have been, on the other end, there have been n-body simulations, which basically amount to doing counting problems, which is to say that we can simulate a full hydrodynamical simulation of what the subhalo populations look like. And then we're just going to count how many objects we have within like a 50 kbc radius of the center of the galaxy. And in general, this is kind of useful for things like GD1, which is within that radius, because then these objects within 50 kbc give us a way of looking at how many possible interactions we should expect. But both of these methods have their drawbacks. In particular, if you do the analytic side of it, you can relate the stream and gap properties to each other, but you basically have no information about like populations. You don't know subhalo populations, you don't know the expected impact geometries that you should have, you don't know their phase space distribution and things like that in general. And then on the other side, n-body simulations can nail down these distributions and give them to us, but for one, some simulations will often just have trouble producing gaps or producing streams to begin with, because the scales of a large box that's doing something like the Milky Way and trying to get it to produce a stream from an object that's much smaller, that's just generally a computationally difficult problem to do. And even if you can form these streams, once you have them, trying to produce gaps and accurately model these is also just an even harder problem. So both of these approaches, they give us benefits, but they also have respectively their own drawbacks. So the idea is, can we somehow leverage the power of both of these approaches, right? And this is where the semi-analytic approach comes in. So essentially, there's a happy medium of these semi-analytic tools, things like SatGen or Galacticus or other SAMs that exist, and they basically generate various Milky Way-like realizations, and they seed initial distributions of subhalos and then evolve them in the host potential. And the upshot of doing something like this is that compared to like full-blown n-body simulations, these things are extremely fast. So just on my laptop over the course of a week, I can basically generate hundreds of Milky Ways and do an analysis. And it really helps beat down things like halo-to-halo variance, right? That's one of the things that plague a lot of these large n-body simulations. Is just that because they're so expensive to run, we can only run a few of them, and as a result, there is just inherent statistical fluctuations from one halo to the next, and those are very difficult, to kind of address without basically running suites of large numbers of these n-body sims. And the other upshot is that these semi-analytic approaches are really nice because they allow us to vary other parameters, like we can basically change the disk mass, we can change the halo potential that things are evolving in, we can change the overall mass of the Milky Way, and so on and so forth. So we have a lot more finer control over various parameters that we want to test. And so then, the idea is that performing kind of these robust population studies is crucial in critically evaluating kind of the extent to which CDM subhalos can create these observed features in streams. So in particular here, just off of one realization, this is a plot of delta mm in kilometers per second, or log of that, versus log f peak. And basically we see that for a CDM like halo, you have most of your power down here, which is basically very, very soft perturbations that are occurring over kind of a larger portion of the stream. And then in particular, this red one that I've circled here is actually this event that I simulated here. And as you notice, it was kind of in the bottom right, so it's something that was extremely concentrated and also produced a very large kick. And therefore, you can kind of very clearly see a observed feature, right? But in general, we can kind of do this we can do this kind of robustly by basically running tons of Milky Way realizations. And the other upshot is that if you look at these two variables here, delta mm and f peak, to some extent, they don't actually care about the underlying subhalo that's causing it, right? So I could put in an SIDM subhalo with its own mass distribution, and it'll give me some set of variables for delta mm and f peak. So kind of going backwards, there's lots of different models that we can constrain just by looking at the distributions of these two variables.
Right, sorry, could you go back one slide? Because you're almost there. So here, just to understand, so you start with the realization or the phase-space distributions from the simulations, and then for each point, you basically use the analytic modeling of the disruption and the gap reduction to get to this spot. Is that the idea?
So you can actually do a little bit better than what a lot of the older analytic approaches did, and the reason is that these older analytic approaches, essentially what they did is worked in the impulse approximation and took an infinitely long stream, an infinitely long and infinitely cold stream. And what you can do is, first of all, streams are not infinitely long. They actually have curvature, and their radius of curvature is oftentimes small enough that you can essentially it's really breaking down, like treating it as like an infinitely straight line. Like that's not a good approximation to realistic streams. So in particular, GD1 actually, that would fail for GD1. The other thing is that streams are not infinitely cold. They have some inherent velocity dispersion. GD1 is pretty cold, so that one's not as bad of an assumption. And then the other thing is that they work in the impulse approximation. So what we do actually is to kind of go beyond all three of those. So we do a little bit of a combination of all three approaches. So we do semi-analytic approaches to determine the subhalo populations. We do kind of like an analytic approach, which is these curves here. They can be analytically computed by actually just integrating the acceleration as a function of time for the entire subhalo orbit, and then decomposing it into the three directions. So you can get these velocity curves just by actually computing what the impulse imparted on the stream is. And then the n-body simulation part of our analysis is actually, once we identify, so we use that as like an initial cut to cut down the number of events that we need to simulate through an n-body simulator. And then what we do is Adrian Price-Whelan has a code called GoLab, which basically does n-body simulations of a stream and a subhalo going by perturbing it. So what we do is once we select on which subhalos we actually want to run through that entire stream analysis, we run it through that n-body simulator, which basically kind of populates a stream as it evolves in the host potential, and it takes into account this perturbation. So I'm brushing a lot of that stuff under the rug because it's very detailed, and it's also some of that stuff is still preliminary, so I'm not flashing some of those plots. But in general, that's kind of our approach, is to basically identify events of interest by doing kind of the more analytic side of things, and then once we have that, actually running it through a full n-body simulator to really determine, you know, what the gap properties look like in a GD1-like stream. Okay, so I'll quickly summarize. So in the first part of the talk, you know, I really talked more about kind of the theoretical understanding of how to do this EFT more systematically, and we basically, you know, had a few steps, which was one, we wanted to use the quantum field theory to set these boundary conditions, and once we have those, we can match onto the underlying quantum mechanics theory, and, you know, solve out to infinity, and it reproduces the exact results that we already know for the Yukawa potential, but it produces genuinely new results for the pseudoscalar potential, which we can understand both heuristically and by actually, you know, computing the Feynman diagrams and seeing that this effect should be what we expect. And then the other thing is that in general, QFT sort of produces very like non-generic potentials. There's a lot of kind of this operator behavior that comes in the form of like different angular momentum modes being coupled to each other, such that none of these infinities or, you know, singularities are really manifesting. And then, you know, once we know how to calculate these things, we can look at where these effects manifest. And two of the places that we would expect it to manifest on very small scales are the subhalo mass function and you know, the density profile of these objects. And we argued that, you know, streams are really good at getting after a lot of these things which we can't look at observationally. So currently we're in the process of kind of doing the CDM baseline, but once we have that, we can then move on to doing the SIDM analysis, kind of top to bottom, and that'll give us a way of constraining, hopefully constraining other regions of the SIDM parameter space that, you know, haven't been looked at when you look at things like dwarf galaxies or clusters and things like that.
Any questions for Aditya?
For SIDM streams, can you say anything about angular dependence of the cross section?
Good. I think the short answer is no. I think the only thing we'd really be able to get after is the velocity dependence. And the reason for that is you're really only sensitive to things like the mass and essentially like the density of the thing that's doing the perturbing. And that's going to be largely dominated just by the velocity dependence of the cross section. So as your velocity dependence gets sharper, smaller objects are going to feel like have a higher cross section, and they're going to collapse more. And you're to a large extent insensitive to like the actual angular dependence of that cross section. So that would be a little bit harder to tell.
We were talking a little bit earlier about some of these streams may have like a dark matter component, but you know, they were coming from the clusters, they were just stars, right?
Yeah.
Like you had a plot showing an overlay of all the streams that we've seen. Are those all stellar streams, or those potentially have dark matter in them? And like if they have dark matter, right, as we talked, maybe that could also change if you're considering non-cold dark matter scenarios as well.
Yeah, good. So as far as I understand, these are dominantly all just stellar streams, with the difference being that they're not all globular cluster streams. So I think this also includes some of the dwarf streams that are there. So in general, globular clusters tend to be more more normal baryonic matter dominated objects, whereas dwarf streams actually have a larger dark matter component. So some of these streams may have an associated dark component going through it. Now, in all of these like in our analysis, even in the SIDM analysis, to leading order, we're not going to take into account the SIDM interactions between the subhalo and the actual stream. And to a good approximation, that's going to be okay, because in general, the dominant effects are going to be things like ram pressure stripping, which are going to be with the entire halo acting on the stream, as opposed to like one of the subhalos in the entire halo acting on the stream. So the dominant effects are going to come from things like that. And the other thing is that stream formation itself is not something that's well understood yet. And so adding in dark matter interactions is only going to complicate that story, and I think people don't have a good sense of how these things essentially form. Like they don't know the role of like the underlying black hole and like what that does to form the stream. Like does it help with the ejection of stars, or does it not help with the ejection of stars, and things like that. So that is an open question, and that's something that we're gonna try and convince simulators to actually like work on is, if you include self-interactions, how does that affect like stream growth and things like that? Because to really do like a top-down SIDM analysis, you do need to take these effects into account. But yeah.
Right, so sort of building up that, right, like you already had a lot of degeneracy in how these gaps form depending on the subhalo properties, right? And you can't measure everything, but then you also have all this uncertainty in the baryonic physics that go into forming the stream. And if I saw a gap in 10 years, a single one probably wouldn't be enough, right? Even if you found that you could fit some like subhalo mass function, something like that to that, like you probably need a very wide sample of gaps to actually say something that would be statistically significant, and that could overcome all these uncertainties in the baryonic physics too, I would guess.
Yeah, so if you want to like robustly say something about the underlying kind of dark matter physics, I think you would need to be able to actually do a full-blown like population study of all of these streams. With that being said, if you just take a look at GD1s, there have been some papers that have tried to address this and try to kind of account for a lot of these degeneracies that occur. In particular, one of the largest ones that they tried to address is the degeneracy between time evolution and the size of the perturbation that's imparted on the stream. And essentially, there's like a whole bunch of standard model things that exist in the Milky Way which could do this. So things like giant molecular clouds, or basically just other subhalos that are not dark but just like objects that we expect to see. And I think, or like globular clusters, for example, also. And I think the short analysis of that was the short conclusion of that paper was that none of these objects would be able to produce the features that are observed in GD1. So it needs to be something that kind of goes beyond a lot of like the standard model things we know and expect to see. And in particular, it also needs to be something that's more concentrated. So CDM halos in general tend to be a little bit puffy compared to things like SIDM halos because of this core collapse that's occurring. And one of the conclusions in that paper, which you can argue how robust it actually is, like statistically robust it is, but one of the conclusions of their paper was that the CDM halos in general would be too puffy to actually cause the gap that we see in GD1 and associatedly the spur in GD1. And it needs to be something that's a little bit more concentrated. And so that was kind of one of the conclusions that sort of prompted people to start thinking about like whether SIDM can actually cause this or not.
Just something quick. So it looks like the main thing, as we also discussed now, that you're sensitive to are all these mass functions, right? Like in some sense, you're a bit agnostic about what the microphysics of dark matter is and so on. So just wanted to get a sense, let's say you take some CDM mass function, you modify it by a factor of 10. Do you have a sense of like whether that would impact these things significantly, or a factor of 10 modification could be, is not visible? Just to get a sense, like in what level of sensitivity we might have.
So a factor of 10, I think, might actually already be ruled out, and the reason I say that, so this is going off of just kind of like what we have seen so far when we're doing our analysis, which is that if you increase the number of subhalos at like every mass decade by a factor of 10 or something like that, obviously let me go back to, so obviously in general, you don't have a lot of subhalos of 10 to the 10 or 10 to the 11. If you were to increase that artificially by a factor of 10,
Yeah, more
You're-
like in the low mass regime.
yeah, what's going to end up happening is at some point you're like in this 10 to the 7 or 10 to the 8 regime, what's going to end up happening is the number of interactions on a GD1 like object is going to increase essentially like the cube root of the number density. And what's going to end up happening is you're going to have multiple gaps in GD1 because these collisions are just going to be more frequent. And they're going to be roughly of the same size. And what ends up happening is the fact that we've only seen one gap in GD1 would basically start ruling out kind of artificially inflating the subhalo mass function. So what you really want to get at is figure out how frequent these collisions are, and if these collisions, if you kind of artificially inflate the number of subhalos that are in the Milky Way, these collisions are going to become more frequent. The other thing to point out is that all of our analysis and conclusions are based literally off of GD1, but there's at this point like 100 streams in, and it's only going to get better with like Rubin and LSST and things like that. So you'll be able to start breaking a lot of these degeneracies by doing more of a global analysis, and that's essentially one of the follow-ups that we're thinking about is right now we have two good candidates, which is GD1 and PAL5, and that's basically just because those are the only two that have good distribution, like good measurements of like the velocity dispersions and things like that. But once we start improving that in like the coming decade, we should have additional candidates that are better at basically dissecting this. And in particular, you can sort of also look at like radial dependences, like as you go further out, how like are there differences in the radial dependence? Like you can start asking all of these more complicated questions and have additional handles on like the underlying carbon physics.
Any last questions? Not, let's thank Aditya again.